Okay. Well, let me start by thanking Lars and the KITP for the invitation to have this program here. It's really been great so far, and particularly exciting to have so many junior as well as not so junior researchers here tackling what problem I'm going to tell you about. So people have asked me, what does particlegenesis mean? And I'm going to try to tell you what that means. And, if I can, particlegenesis. What we really want to know is why there is more matter than antimatter in the present universe. And so what I want to try to do in this talk is really three things. I want to explain why this is a problem. I want to try to give you at least a sketch of some of the proposed solutions and their context. And by context, I really mean the context of the cosmic history, and then try to give you at least a flavor for some of the open problems and questions. And I'll try to do that a little bit in general and with a couple of specific examples depending on how our time goes. Okay. And as I understand, the spirit of these talks is to be interrupted. So I'm happy to get through 2 pages of my notes, and that won't be offended if that's all we do in the next...
interrupted by the other programs. Your program should contain themselves.
They should, but given the excitement, I'm not sure that they will necessarily do that. So let me start by just sketching what the problem is. And some of this may be familiar to people here, but nonetheless, I like to start relatively simply. So the problem has to do with this rather well-known picture of the cosmic energy budget, which today looks something like this. We know from various observations, most recently Planck, that about 68% of the energy density of the universe is dark energy, dark E. About 27% is dark matter, and about 5% is the visible baryonic matter. And it is long known that we really can't explain where this 5% came from. We tend to hear a lot these days about the dark matter, and it certainly is, of course, a huge mystery what the dark matter is and what its interactions are. But we shouldn't forget that explaining even the origin of the visible matter remains an unsolved problem for particle physics and cosmology. So we'd like to know where this 5% came from. It's also rather puzzling as to why the energy density associated with the baryonic matter is not too different today from the energy density associated with the dark matter. It's not a number of order hundreds. It's either order 1 or order 10, depending on how you count 5. Okay, so but that's not so different. And I'm not going to say anything about the dark energy. It could be cosmological constant, or it could be something else. Now, the baryonic matter is characterized, often is characterized in terms of the ratio of the baryon minus antibaryon number density, which I'll call NB, over the entropy density of the universe. And that number, if we take the recent results from Planck, is 8.59 plus or minus 0.11 times 10 to the minus 11. So that's a really small number in this way of characterizing things. There's not many baryons compared to the total number of degrees of freedom in the universe, but nonetheless, for us, it's clearly an important fraction of the cosmic energy budget. So you can ask, why not just assume that this was part of the initial conditions of the universe? And most people think that's unlikely because inflation would have inflated away. And so I'm going to disregard this possibility and concentrate on the other possibilities, which is that there were some dynamics of the early universe that generated non-zero YB. Okay? So what do we know about what those dynamics had to be? Well, the starting place for that discussion goes back to observations by Sakharov in 1967, who identified 3 ingredients in the fundamental physics of the early universe that had to be present to get something from nothing. Okay? What were those ingredients? Well, the first is that total baryon number had to be violated. That's a pretty intuitive one, given that we have a non-zero baryon asymmetry. The second is that the symmetry called charge conjugation and something called charge parity symmetry both had to be violated in the dynamics of the early universe. And the third is that at some point in cosmic history, the dynamics had to go out of equilibrium, or the combined symmetries of charge, parity, and time reversal had to be violated. Now, as I said, this one is pretty obvious. The reason for C and CP violation is that if you think about microscopic elementary particle physics interactions, you need to generate an asymmetry somewhere. And so C and CP violation are needed to generate asymmetries of the form where, let's say, a particle A decays to particle B plus C. And in order for that rate to be different for the antiparticle reactions, C and CP have to be violated. Now, what about the third Sakharov criteria? Well, there's again a kind of a simple argument that I like to use when explaining this to people about why you either have to go out of equilibrium or have CPT violation. And the argument is the following. The number density of baryons, very roughly, is going to go like the quantum statistical average of the baryon number charge, which I call B hat. Rho hat is the density operator. And so let's ask how this average behaves under the symmetry CPT. So let's let gamma denote the combined operation of CPT. If I now insert gamma minus 1 in a couple of places, I can write this as the trace of gamma minus 1, rho hat gamma minus 1, B hat gamma. And one of the things we know about the baryon number density, it's a vector charge, is that it is odd under CPT. And so the transformation properties of NB will then depend on the transformation properties of rho. Now, if we're in an equilibrium situation, then rho goes like e to the minus beta h. And if h commutes with gamma, then gamma inverse rho gamma is equal to rho. And we see that the baryon number density has to be minus itself, and we get 0. So what's the solution? The solution is either this has to be violated, the symmetry has to be violated, or we have to assume that we're not in an equilibrium situation. We can't write down rho as an equilibrium distribution in the first place. Usually people focus on this possibility, and in the rest of my talk that's what I'm going to focus on, but we shouldn't forget that it is certainly possible, although there's no evidence for it, that CPT was violated in the early universe. So,
did Sakharov make the CPT argument as well?
Well, I don't recall it being in Sakharov's paper, but it's well known these days that you can violate CPT. I know you're interested in CPT. Okay. So, in the interest of time, I think I'll skip over the next sort of aside, which was people ask, maybe the universe is actually antibaryon symmetric, but it's sequestered. And there are arguments why that doesn't work. And if you're interested, maybe at the end of the talk, we can come back to that. What I'd like to do is actually discuss the proposed solutions and put them in their sort of cosmic history context. So let's go to proposed solutions.
You assume up to now that the baryon charge is conserved. I mean, in order to say that the nickel could do it, or in order to say there's a charge there.
Right. Once you've violated baryon number somehow, to keep it violated, that's really what I've assumed here. Yes. There are scenarios with spontaneous baryon number and explicit baryon number violation and topological baryon number violation. You have to violate it at some point. But after that happens and some asymmetry is generated, why doesn't the statistical mechanics of the universe wash it out? And it has to prevent the washout, either you have to go out of equilibrium or CPT has to be violated.
But this argument with CPT implies that baryonic number behaves like you said, right, under CPT, right?
Right.
If baryonic number is violated, why it should be the same way as vector B?
So I kind of made a sort of time sequence thing. I said at some point B is violated, and we'll see concrete realizations of this later on. And either in order for the actual charge that's generated, that's measured by this operator, to remain non-zero, it can't be washed out. So something has to prevent the washout. Okay.
Right. But the argument of CPT is based on that it's equal minus B, right?
Yeah.
This itself could be violated.
Yeah, it could.
But gamma squared is 1, so it can either be +1 or -1. It can't be violated by a little bit.
Yeah.
More than that, Michael.
Thank you.
Okay.
We've got wine and cheese later on. So I think this would be a good point for a discussion. So let's talk about some of the proposed solutions.
Could be a mixture.
And I want to do this by making a timeline here. Let me see if I got a bigger piece of chalk. So you'll pardon my poor graphical skills, but I'm going to make a timeline to try to put in context the various solutions to this problem. So this is the time axis going down. This is the Big Bang starting here. We live down here today. And we can characterize different eras in cosmic history by either the typical energy scale, the temperature, or the time. And I'm going to measure time mostly in seconds, temperature in Kelvin, and energy in GeV. So the earliest history era people talk about is the Planck era, which corresponds to something like 10 to the minus 49 seconds post-Big Bang, temperature of 10 to the 32, energy scale of 10 to the 19. So if you bear with me here, I'm just going to fill in the rest of the timeline and put the scenarios on it. Somewhat lower scale for later time, 10 to the minus 37 seconds, is the gut scale. So that's energy order 10 to the 15 to 10 to the 16th. This is not a very good log scale. We're going to make a big gap here down to the Electroweak era, which is about 10 picoseconds after the Big Bang, 10 to the 15 Kelvin, or 100 GeV. A little bit lower is the QCD confinement era, which is 10 to the minus 5 seconds. This is 10 to the 12th Kelvin, or something of order the pion mass, 10 to the minus 1 GeV. A little bit later on is the era of Big Bang nucleosynthesis, 100 seconds after the Big Bang, 10 to the 9th, 10 to the minus 4. And then we finally got something I have to convert to years, 3 to 4 times 10 to the 5 years, or 3,000 Kelvin, or 10 to the minus 4 seconds is sort of the era of recombination. So let's just put these monikers here. The Planck scale, the gut scale. This is the Electroweak scale. This is a Klein mass. This is, I don't have a very good one for Big Bang nucleosynthesis. It's sort of nuclear scales it a little bit. Ionization energies sort of correspond here.
So those are both 10 to the minus 4?
10 to the minus, sorry, this is 10 to the minus 10, thank you. Clearly not. Okay, so now we think we now believe that even more strongly that inflation happened in the early universe, which is somewhere in this range here. And at the end of inflation was an era associated with something called reheating. Around the electroweak scale, at this temperature I'll call T electroweak, is when the Higgs mechanism became active.
Michael, you don't seem to have leptogenesis in the...
I haven't put any scenarios yet.
Yeah, but I don't see...
I didn't put that number yet. I'm gonna put
okay.
arrows in. Just bear with me a few minutes. And as I said, down here is the era of Big Bang nucleosynthesis. Light elements were made. Somewhere in between was the decoupling of radiation and matter, and this is recombination. People who think about things. Now, scenarios. So one of the most natural scenarios is something called gut baryogenesis. Baryogenesis means getting baryons from no baryons. It's really Particlegenesis. And that somewhere is in the gut scale. These days it's disfavored because of inflation. In other words, for the same reason that we think if there had been an initial baryon asymmetry, inflation would have wiped it out. Gut baryogenesis is sort of pre-inflation, and so it would have been, any baryon asymmetry would have been inflated away by the time we got to the end of inflation. So these days there isn't a lot of discussion of gut baryogenesis. Now there are people who talk about inflationary scenarios. Hasn't been focused on a lot lately, but maybe in light of the bicep 2 observation, claim of an observation, it will get more attention. We haven't so far discussed a lot about inflationary baryogenesis. Somewhere in reheating and post-reheating, there's a very sort of beautiful scenario called Affleck-Dine baryogenesis, which I may say something about toward the end of this discussion. And somewhere in this sort of range here is what Carlos had referred to, leptogenesis. And that's one of the examples I will try to do in more detail. And I'll call this standard leptogenesis. It typically is a high-scale, early-time scenario. Now, let's come down to the Electroweak era. The poster child for baryogenesis scenarios that would be active around T electroweak is Electroweak baryogenesis. Not much mystery about the name of that title. But there are other scenarios that could have been active at the Electroweak temperature, something called low-scale leptogenesis. Another class of scenarios which aren't baryogenesis scenarios per se, but they try to relate baryonic matter and dark matter, called asymmetric dark matter, ADM, and they could have been sort of active around the Electroweak scale. Okay, so I'll come back to say a few things about these in general in a moment. Then there are some lower scale possibilities. This timeline is the sort of standard cosmological history, but if you assume a non-standard cosmology, non-standard thermal cosmology, you might be able to lower the Electroweak temperature and get something called cold Electroweak baryogenesis. And something that may make some more sense to you later on, the terminology, also goes in this sort of lower scale scenario, is called post-Svaleron baryogenesis. And I won't say a lot about these because they haven't been as much the focus of research as some of these others. But just to lay out this landscape. So the questions that we ask are, in this whole menu of possibility, which scenarios are viable? And viability has a number of considerations. Which, if any, are testable? And how well can we calculate the baryon asymmetry in these various scenarios? Okay, so there are sort of model building considerations, phenomenological considerations, and really formal technical theoretical considerations that go into this problem. Now, one other comment I want to make before I go into some illustrative examples is that these sort of Electroweak era scenarios, I think, are taking on added interest now because we have prospects for data that will constrain or test them, possibly rule them out. And so to my mind, if life is good, experiments will give us the ingredients that say, aha, this is where it's happening. But if not, perhaps at least we can kill one class of scenarios. And then it's either going to be something really exotic at very low temperatures or some of these earlier time scenarios that are in general harder to test. Okay. So the Electroweak scenarios and to a lesser extent standard leptogenesis have some phenomenological handles that make them quite interesting to work on. So let me pause and see if this sort of general sort of setup provokes any other questions or comments, or go on. No?
You have in mind LHC data, or?
LHC, but not only LHC. So, in fact, I'll make an advertisement for today's talk. Jerry Gabriel's, well, let me first say, there's, of course, the collider LHC, E plus E minus, possibly a future 100 TeV PP machine. But there's also low energy experiments, and in particular, searches for permanent electric dipole moments of elementary particles or systems of particles provide a very powerful probe of the second of Sakharov's criteria. And I'll explain why looking for new CP violation is important. So people have probably heard a lot more about the collider aspect of things, but I think one reason why I'm so glad that Jerry could be here today is that I think people should be aware of the importance of these early tabletop experiments that are probing similar energy scales and are crucial for at least testing one subset of these baryogenesis scenarios. All right. So I'm going to try to leave the menu up over there and do the rest of the talk over on the boards on your left.
Can I ask about this inflation versus gut scale thing? Is it impossible to put the inflation scale high enough for it to work, or is it just disfavored?
Well, as I understand the bicep interpretation, the sort of scale of inflation is sort of around here. And so, it's a measurement that's somewhat controversial now. There's something called foregrounds that people are debating whether it's really true. So I don't know that if it's totally impossible, but...
The bicep was putting up higher than people expected, right?
Yeah, but you would have to put it up really high, I guess, or bring the gut scale down, and then it's not the gut scale. So it probably would fall in one of these other sort of scenarios here. But I haven't personally worked on those scenarios a lot to give you a more informed answer than that. Maybe someone else here would want to comment. Okay, well, let me do a couple illustrative examples. The two that I'm going to illustrate are standard leptogenesis and Electroweak baryogenesis, because I think that's where most of the activity has been over the years and much of the activity in our meeting. But I'll make the comment that these asymmetric dark matter scenarios really rely on a lot of the ideas that appear in these sort of example scenarios. So I think it's good nonetheless to pick these two, at least to start, for people who haven't been familiar with this problem. So, illustrative examples. And we'll start with leptogenesis. And leptogenesis is well loved by theorists because it's simple and elegant and speaks to the solution of one of the important problems in particle physics, which is the mass of the neutrinos. So the motivation really derives from the following fact about nature. We know that neutrino masses are not zero, but they're very small, at least smaller than about an eV, which is much smaller than all other elementary particles except for the massless ones that we know about. So one of the most sort of popular and really elegant solutions to explain why this sort of disparity in mass scale exists is something called the Seesaw mechanism. And what does the Seesaw mechanism say? Well, in its simplest incarnation, it says there are really two classes of neutrino states in nature. There are left-handed neutrinos that interact with W's and Z's in the Standard Model, and then there are right-handed neutrinos that don't interact with the W's and Z's. I'm going to give them different labels. And the right-handed neutrinos are going to have the property that they can be their own antiparticle. So if we write down the mass matrix, the mass Lagrangian for these states, it looks like this. And I'm going to put a 0 here. I'm going to put something called the Dirac mass in the off diagonals and something called the Majorana mass in the lower right. And if you diagonalize that matrix, you find that there are two states. There's a light state whose mass goes like m Dirac squared over m Majorana, and a heavy state with mass of order mn. So you can work out, therefore, that given what we know about neutrino masses, mn has to be on the order of 10 to the 9 m Dirac squared, where that's measured in GeVs, the GeV. Okay. So if Dirac mass is sort of order 1 in units of GeV or higher, then the mass scale associated with these heavy states is sort of up here. Okay, that's why this scenario is going to correspond to an early time or high scale scenario.
Okay. Michael, in what sense it's right-handed if it's massive?
In what sense is it right-handed? If I write down a two-component spinner, it transforms under the.
No,
I mean, I don't know if you want to give it an answer.
no. It's a denomination.
No, I mean, left-handed and right-handed is well defined for massless particle, right? Not for massive.
You can always project out of a four-component spinner a two-component.
Physical particle, it's not.
The physical particles are the physical particles are the light and heavy states.
Right, and the heavy state has spin 1/2, so it's two states, right?
Yep.
Okay, which one of them is right-handed, which one is left-handed? It's not possible to define, right?
At that point, yeah.
No.
Yeah, but
yeah. So the name is
the name is what is used before mass diagonalization.
That it has the quantum numbers of what the right-handed neutrino will have in a standard model. That is.
But the chirality is well defined even with the mass. Just chirality is not the same as helicity.
No, chirality there is no chirality for massive as well. You know, it's a massive particle, right? It's a
clearly. So I'll call this the light neutrino, and this the heavy neutrino, and from now on, we no longer have to have this debate over terminology.
No, I understand.
But the denomination comes from the fact that if you
would have a right-handed
to 0,
right,
would be the right-handed component.
Exactly, and it would be sterile with respect to all the standard model.
But then it would be massless, right?
Correct.
Yeah. So it starts off.
Mass with the Dirac mass. with the back expectation value of the Higgs.
How are the dimensions in that formula supposed to work? 10 to the 9 times a mass squared times...
Well, I said it quickly. It's mass in GeV squared. Okay.
Some charge conjugate missing there, so you cannot...
Where am I? Somewhere.
Probably near left.
You left. Yeah.
No, yeah.
Here.
Yeah.
Upper right.
Upper right. Thanks.
Because should be right.
Yeah. All right. Yes. Thank you. So this origin of this Dirac mass term is going to be important for the leptogenesis mechanism, and we can think of it in Feynman diagrams as coming from the following interaction of a Higgs field with n sub r, note that I didn't use right, n sub r, nu sub L, and when the Higgs gets a vacuum expectation value, you generate this m sub d. This will come with a coupling constant I'll call lambda, so-called Yukawa coupling. Okay. So the mechanism for generating an asymmetry arises from the fact that we have two kinds of decays that can occur. You can have the decay of n sub r to L and H with lambda, and we can have the decay n bar sub r to L bar and H star with coupling constant lambda star, but n bar is equal to n. And so this, in principle, if the coupling constants are slightly different, then there can be a different rate for the n and the n to decay to the different sets of final states. So this set of final states has total lepton number plus 1. This has total lepton number minus 1. And if lambda does not equal lambda star, that corresponds at the formal level to having CP violation. So you can have an asymmetry in the rate for the decay to the two different final states. And that's part of where Sakharov, which I erased, comes in. Now, it's actually a little bit more complicated than that. If all we had were these so-called tree-level decays, we would still get zero asymmetry, it turns out. And so maybe I'll go over here. Yeah, I can erase this now.
Michael, can I ask quickly? So if the I was trying to think, as the limits on the neutrino mass get more stringent, do you start getting uncomfortable with this scenario or not?
Not really.
It's changing your energy scale, but you've got so much room.
You've got a lot of room with lambda. Yeah. It's, what's really trying to do is explain why lambda, if the mass mn would be weak scaled, and lambda would have to be really small, and that seems unnatural to people. And so you push this mass up to 10 to the 9 to 10 to the 12 GeV, then lambda isn't unnaturally small. But then if it's 1 eV total, mass versus 0.1 eV, you're changing maybe an order of magnitude or two on 10 orders of magnitude. So it's not so uncomfortable. Although in different scenarios the devils are in the details, but in this case, so far we aren't too worried. Okay. So I said life was a little more complicated than this. In fact, to get a real asymmetry, non-vanishing asymmetry, there has to be an interference between a tree level and a loop level decay. So n right goes to LH, and then there is, and now I have to introduce more than one species of n sub r, so I'll put a label, nr1. And R1 can then fluctuate through a loop into L and H, into another species, nr2, which can decay. And there are also so-called vertex corrections, which I won't write down. And so we've got different coupling constants here. We've got lambda 1, lambda 1, lambda 2. And it turns out if you work out the rate for the asymmetry for N1 goes to LH minus N1 goes to L bar H star divided by their sum. That's called epsilon. And that basically goes like the imaginary part of lambda transpose squared. Okay. This is a consequence of unitarity in CPT, something called Weinberg-Nonopoulos theorem. Basically, it's an interference between the CP violation and the Lagrangian and the absorptive part of a one-loop decay. Okay, and that's what's required to get a non-vanishing asymmetry. Now, how do we contend with where does the Sakharov out of equilibrium criterion come into play? Well, the problem is that you can have inverse decays. So H and L can annihilate to N1. Okay, so something like this. That's supposed to be H, goes to N, and I'll just generically label it as N. And then N could decay to L bar and H. Okay, so you can take H star rather. Take, the state with lepton number +1 and turn it into a state with lepton number -1, and that can wash out any asymmetry that you have. So you have to somehow contend with this washout problem. And so the requirement is that the rate for the washout has to be out of equilibrium compared to the rate for the decays. Say that maybe a little bit more clearly here. So if we have a Hubble rate, expansion rate of the universe goes like H, and we have the rate for the decay. H is Hubble. Let's see, how am I going to... Yeah, what am I going to do? I don't want to call it H naught H. Little h. Let's call it script H. There, okay. Thinking on my feet, I got to tell you, notation kills me every time. Okay. Then we've got the rate for the decays is going to go like this lambda squared times the mass of the decaying state. The Hubble rate typically goes like temperature squared over the Planck mass, and I'm neglecting the G star factor. And the inverse decay rate goes like the decay rate times a function of the mass of the neutrino over the temperature, which is coming from statistics. And so if the universe cools enough, then the inverse decay rate can be suppressed with respect to the decay rate. And so the lepton and Higgs aren't as likely to find each other to wash out the asymmetry as the neutrino is to decay to the lepton and Higgs in the first place. And so what you find is that for temperatures sort of order 10 to the 9-ish GeV, this rate is less than gamma sub H. I'll call it Hubble. And so we go out of equilibrium. Now again, there's a lot of devils in the details, but that's sort of the basic mechanism of generating a lepton asymmetry. Okay, so that's not the baryon asymmetry. We get a baryon asymmetry.
Does that
Yes.
asymmetry always have one sign?
Does it always have one sign?
Well, it depends on the phase.
Depends on the phase, right? So we want it to have a certain sign.
Yeah,
so
I know, but
So it doesn't have to have had that sign. It's a good question. So let's talk about how we get this lepton asymmetry into a baryon asymmetry. And the culprit for that is something called the Electroweak sphaleron. Now I'm going to assume that many people here have not heard of a sphaleron, or if you've heard of it, you don't know what a sphaleron is, so I'm going to explain to you in a very cartoon level sort of way what a sphaleron is. And one way to think about it is to plot the energy of the universe. I keep breaking this chalk. E as a function of the gauge fields in the SU2 cross U1 theory, the SU2 part in particular. And what you find is that there are an infinite number of ground states. This goes on in either direction. And up to factors of constants of proportionality, the difference between the ground states is characterized by a difference in the total lepton plus baryon number. Okay, it's something called Chern-Simons number in formal terms. Okay, so what a sphaleron is the gauge field configuration that lives halfway between two minima. Okay, it's actually gauge plus Higgs. And so you can think of the following. You could imagine if we were at zero temperature and the universe were here, there would be some probability to tunnel to a neighboring ground state. That probability goes like e to the minus 4 pi over g squared. That number is really small, and so that's a rate that's too slow for anything to happen on the time scale of 13 billion years. On the other hand, at finite temperature, you can excite these sphaleron configurations, and some of the time they can relax back to the state you started in, or they can go to the neighboring one and change baryon plus lepton number. So that's known as a sphaleron transition. And when a sphaleron transition occurs, it's kind of like hopping over the barrier, then you change total B plus L. Now, there's another cartoon that people write down that's really traced back to the paper by Tufte on instantons to think about this in practice. What a sphaleron transition can do, for example, again, do my best to write this down. It sort of relates changes in the number of up-handed left quarks, down-handed left quarks, two of them plus the other generations. So there's the charm and top. And then, so I'll stop here with the top left. And then I can have the three generations of neutrinos, nu E, nu mu, and nu tau, all left-handed. And the total charge in this process is 0. And so if you start with an incoming set of left-handed neutrinos that were generated by the lepton asymmetry, then a sphaleron can turn them into an outgoing set of left-handed antiquarks and change the baryon number. So it can turn the lepton number into baryon number by hopping over this barrier. So we need the sphalerons to be active in the early universe to convert the lepton asymmetry to the baryon asymmetry. Okay? Eventually, below T electroweak, the sphaleron processes become energetically disfavored, and the baryon asymmetry that's made by this leptogenesis to baryogenesis process is frozen in, and that's what we see today. So that's sort of, in a nutshell, how leptogenesis works. Some of the questions that one can ask are, how testable is leptogenesis? It's a high-scale scenario. The ends, the heavy states, have masses 10 to the 9 GeV or so that you can't make in a laboratory. Are there any ways to test this scenario? There are some indirect handles. One is the light neutrino spectrum and interactions. The other is to search for the fact that the neutrino is its own antiparticle, an experiment called neutrinoless double beta decay. So if that were to see a non-zero signal, that would tell you lepton number is violated, and that would at least be circumstantial evidence that there was something violating lepton number that interacted with neutrinos in the early universe, and therefore leptogenesis would have a stronger sort of phenomenological basis. But it's a very pretty and relatively simple idea. Okay? Now, one other set of questions with leptogenesis is that it doesn't always have to happen at the high scale. And so people are thinking about the possibility of low-scale scenarios. Are they viable? Can they be tested? And there are a number of possibilities there that I won't have time in this talk to tell you about. So let me, I know we're at 1. I can continue to go a little bit. Let me sketch out the other, which is this poster's child for the testable scenarios, the Electroweak case. And I think that'll suffice, I hope, to give you at least a flavor of the kinds of things that we're thinking about in this program here. keep our friend the spaleron because they're going to be critical. So, Electroweak baryogenesis, I think of it as a very rich scenario. Some people would say what that really means is complicated. So depending on your taste, you either like leptogenesis type simplicity and elegance, or you like richness. Okay? There's a lot of interesting theoretical problems here. But no one will argue that it is probably the most testable scenario in our menu over on the far right. So what are the ingredients for the Electroweak scenario? One is that the universe went through a first-order phase transition at T Electroweak, and that it was a strong first-order phase transition. Strong to be defined. Strong in quotes order Electroweak phase transition. The second is that there be, again, what I'll call large, in quotes, CP violating effects. Now, in principle, you might ask about the Standard Model. And let me give you a little bit of background about the Standard Model, but first I want to say something about this issue of, in general, phase transition. So the way we think about phase transitions, again, in an oversimplified way, is in terms of something called the finite temperature effective potential, which you can plot as a function of the Higgs vacuum expectation value. Okay, so now I've changed your notation again, Carlos, so you know it's 5. And what we're interested in is the temperature evolution of this potential. At high temperature, it looks like this. So the lowest energy state is at the origin, symmetry is unbroken, and that's where the universe lives. Eventually, the universe cools and a secondary minimum forms away from the origin. At some temperature, it becomes degenerate with the origin. This is called the critical temperature. At somewhat lower temperatures, it becomes the lowest energy minimum, and the universe likes to tunnel to this vacuum over here. Okay? This is known as the nucleation temperature, denucleated. Okay? Now, this is what a first-order phase transition looks like in this language, and it's characterized by the existence of a barrier between the two phases. It turns out that as you turn up the Higgs mass, the phase history looks more and more like this. Where there is no barrier. And in fact, what we know from the lattice studies of the phase history of the Standard Model at finite temperature is that the maximum Higgs mass, n max h, for a first order phase transition is somewhere just below 80 GeV, which is therefore not, within the purview of the Standard Model. So, bad news for Standard Model Electroweak baryogenesis. But you can still ask, well, what if we had lived in a universe where the Higgs was lighter? Could we have enough CP violation to get the baryon asymmetry? And in the Standard Model, any CP violating asymmetry goes like something called the Yarls-Cobb invariant, called JCP. You don't need to know what that is. Times differences of quark masses over temperatures. And all the generations of quark masses have to come into these differences, so there's really a product here. So I should really write product. And it turns out when you work out the numbers, this is sort of order 10 to the minus 17. So our baryon asymmetry is 10 to the minus 10, and so there's clearly no hope with these scales of getting the baryon asymmetry we see today. On the other hand, just to make a quick comment about this cold Electroweak baryogenesis, if this temperature would be much lower, then this number could be much larger. And so maybe the CP violation in the Standard Model could have done things if we lived at, if the transition were somehow delayed in time to somewhere before the QCD phase transition, but not too far above. Okay. But most people think that's, unlikely. Again, it could be. And so if we want to get baryogenesis at the weak scale, we've got to add something to the standard model. What do we have to add? Well, to get a strong first-order phase transition, we need new spin-zero particles. Okay, things that are like the Higgs or supersymmetric partners of fermions in supersymmetry. And to get new CP violation, we need both new degrees of freedom and unsuppressed CP violating interactions. Okay? The LHC, or future colliders, can look for these. So a lot of our work is trying to figure out what are the scenarios where these would arise and how you might test them. The most powerful probes of these new CP violating interactions, if they live at the electroweak to TeV scale, are these electric dipole moments. Okay? So it's a really nice marriage of very high energy frontier physics and what we call intensity frontier physics to go after this scenario here. I could elaborate on this. Yeah, let me just a few more minutes and I'll be done. Let me now sketch out how the scenario actually works in practice. And I want to leave up our friend here, the sphalerons. So I'm going to erase what's here, and then I'll stop, because it'll lead to the kinds of open questions that we are discussing in the program. So the paradigm for electroweak baryogenesis is that there's a first-order phase transition, and when this tunneling occurs, it occurs via nucleation of bubbles of broken electroweak symmetry. At temperature T nucleate, which is a little below the critical temperature for the transition. So we start in a universe that's electroweak symmetric. Bubbles of broken electroweak symmetry nucleate in this background. They start to expand and eventually fill the universe. That becomes our universe today. Out here, the sphaleron transitions are fast. These hoppings occur very rapidly. Inside, they're suppressed because the sphalerons all of a sudden get a large energy, and it's hard to make them. So the sphalerons are suppressed. And so the out of equilibriumness is satisfied by this nucleation process where sphaleron transitions have different rates inside and outside the bubbles. CP violation comes in through interactions of new left-handed particles with the bubble wall. And very roughly what happens is that these interactions generate an asymmetry that kind of biases the sphaleron picture here to tilt in one direction. So the sphalerons like to make more baryons than antibaryons for a while. And while that's happening, the bubbles are pushing the baryons out, eventually capture them. Once they're inside the bubble, the sphalerons can't run back up and unmake them. And so that freezes in the baryon asymmetry. Okay? So, as I said, the hope then is to look for the new scalar degrees of freedom that would lead to this kind of process, and the EDMs will tell us ideally something about the CP violating interactions. Now there are lots of theoretical challenges, and this is what I'll sort of close with. I don't have time to do specific examples, although I'd love to, but this will hopefully suffice to give you the flavor of the kinds of things we're talking about. We'd like to know what kinds of new fields are needed. To make this work. What was the phase history? How do we compute in a robust way these properties of the phase transition? The critical temperature, the nucleation temperature, the rate for bubble nucleation, the sphaleron rate, very challenging calculations. And there's still a lot of work to be done on those. One of the things that I think this community is contending with is that to study wide classes of models, we have to use perturbation theory, which is, our pen and paper tool of choice. But at some level, one should be skeptical about perturbation theory as a way of understanding phase transition dynamics. And so the robust calculations are going to be Monte Carlo, but those are expensive, and it's hard to investigate large numbers of models in parameter space. So how well can we get guidance from perturbation theory to point lattice people in the right direction in terms of what to calculate? And then we need new CP violation. Where is it? To calculate these asymmetries, one of the big theoretical challenges has to do with transport theory. And why that's an issue is that as the bubble is expanding, the Higgs vacuum expectation values are becoming non-zero, the particle masses are changing. So you have particle propagation in space-time varying background fields. And that's a challenging theoretical problem. Okay? And then we've got the question of how to compute the bubble dynamics. So to summarize, why is it worth working so hard on these problems? I think the reason is that if we really want to confront this scenario with data, we have to have the most state-of-the-art, robust calculations possible. We can't live with order 10 uncertainties. We have to have much smaller uncertainties. And so this is our sort of our challenge theoretically for that class of scenarios. So, okay, it's at 1:15. I'm going to stop. But that's, at least I hope, a flavor for what we're doing in Particlegenesis. And happy to take more questions informally later.
Question? Brad?
Mike, are sphalerons a type of instanton? And are you concerned about zero modes of the fermion operator?
You are. Yes, they are. It's sort of finite temperature. And so when you calculate a sphaleron rate, there's a classical sphaleron in saddle point energy, and then there's a fluctuation about that, and zero modes are part of what you have to worry about in calculating fluctuation determinant. So yes, at some level, you do have to worry about, but they are topological in that sense.
Maybe I can add the zero modes are precisely what of the fermions are precisely what is violating the Perceptor number. So that's precisely the point. Yeah.
So Michael, I couldn't tell in the last scenarios whether there's a naturalness argument or not about omega baryons being order 1. Or is that viewed as an accident? Or
well, so the idea is if you start it with some asymmetry somewhere, it leads to a non-zero chemical potential. And if you have some interaction between baryons and dark matter, here's one. It goes through then the dark matter and the baryons will be in chemical equilibrium, and their chemical potentials will be. And so to that sense, the reason why you might expect the two asymmetries to be of the same size could be naturally explained this way. But why it's order 1 on the pie chart, I think, is probably what you're asking, and not order 10 to the minus 3. I'm not going to give you a good intelligent answer, but someone might. Good question.
Great.
What is the background space-time that the bubble nucleation is taking place in?
So masses in the standard model, let's say the mass of the quarks, are proportional to the Higgs vacuum expectation value. And so if phi depends on x mu, then the quark mass depends on x mu. And that is because the value of the Higgs vacuum expectation value is changing from 0 outside the bubble. So here's phi as a function of x to non-zero inside the bubble. So in this region here, where you're making the transition, m is really a function of space-time, and how you compute transport in that how you do it systematically with controlled approximations that you believe is the ongoing open problem. And some progress, but it's really good progress, but it's still not completely solved.
Okay, well, let's thank Michael again.